Thank you very much. This is probably my either the second or third time to visit here, many years ago, however. So it's a real pleasure to be back. And yesterday I was agonizing over my lecture. First of all, I temporarily lost my memory stick, this one, and then I quickly came up with a substitute. And at that time, I was thinking of maybe a 45, 50, 1 hour lecture or something like that. So I prepared with that in mind. And then this morning, Mr. Eklov miraculously came up with this thing. So I was debating which way I should go. And then I came here only to find out that my lecture is already in store. So I have no choice but to present the same lecture. Okay. I hope not too many of you were there. Anyway, so as you can see, the magic power of transition metals, past, present, and future. But I probably won't have time to talk about future. Besides, it's a halfway secret. And I don't have time to talk about what we do here with the zirconium. So I'm going to have to stick with this nickel palladium domain. And let's see. Yeah, thank you. All right. So as the whole thing started when I went to Philadelphia to study at University of Pennsylvania in 1960. In my life, there's no question. This is by far the biggest thing. But when I thought about what would be the second most critical thing that happened to me as a chemist, then I have to think of, I would cite my moving over from Japan to US as a Fulbright scholar, which I did in 1960. And I stayed there for 3 years and for my PhD degree. And that's the time, during that time I learned most everything in organic chemistry at the professional level. And then I met a number of Nobel laureates and future Nobel laureates, like Professor Woodward and Brown and Corey. So that was a very, very inspiring experience. And I think all these things, experiences, contributed a lot to my presence. And I proved myself to be a pretty good student. Actually, surprisingly good student during my first year. Then I went into the laboratory and I found myself to be a very poor experimentalist. I'm sure many of you feel that way. And I began wondering why organic synthesis is so difficult and so cumbersome. Isn't there a way of just simplifying whole organic synthesis? I was still young, so I came up with this very self-centered notion. And but today I say, when we think of organic synthesis, everybody should think of how to synthesize any organic synthesis. We want to be able to synthesize any, not just this, not that, not this group, any organic compounds in high yields, in high efficiency, selectively, and then preferably economically and safely. So I came up with this YES and ES. YES. And more recently, someone used very effectively this YES. Yes! And then went to the White House. But I think this, if you think of organic synthesis, scientifically, practically, I think these are some of the most important things. And collectively, they translate into green chemistry. There are many, many different definitions of green chemistry, but I think this is the best definition of green chemistry. But the question is how to do. Well, as a student, I thought of this children's Lego game. You have A piece and a B piece, or in organic synthesis, R1 piece and R2 piece. And if we can snap them to form a carbon-carbon bond, that would be, if we can do that at will, and that is probably the most general way of synthesizing organic compounds. And so to do that over the years, I realized that to do that, we have to bring in many talented other elements other than organic elements, which are shown in green, hydrogen, and about 10 of them, 1, 2, 3, 4, 10 of them. So 10 to a dozen, including perhaps arsenic sometimes, but that's toxic. So in addition to relying heavily on these 10 or dozen elements, we have to at least think of whole periodic table, which of course pioneered by Mendeleev in Russia. And yesterday I learned that many of these elements shown here were discovered not far from here. And of course, many other elements, here, pioneers, Berzelius and others, have also discovered, contributed. And in my opinion, we should use them. We should at least consider them all. But of 110 or so, in organic synthesis, radioactive elements, about 26 of them, of course, there are other isotopes, but without talking about that, main one, the radio. So those shown in red, probably we can forget about for a while, at least. And we should also try to stay away from intrinsically toxic. I list 7 of them: beryllium, and cadmium, and mercury. As a Japanese, I know so well how dangerous these are. They're intrinsically toxic. No matter in whatever form, I think I believe they are toxic. Thallium, lead, perhaps even lead. So, and of course we must avoid inert gas for obvious reasons. Then we have, besides these 10, the so-called main group metals in blue, and some of them, such as magnesium, lithium, or alkali metals, those have been used, but I will show you what we can do with these main group metals in terms of this Lego game cross-coupling. And I will show you how advantageous to bring in these golden elements, about 2 dozens of them, especially copper, nickel, palladium, and this time I think we are very pleased that the Nobel Foundation recognizes palladium as the key element, which I believe. I agree. Okay, so before us, this Lego game synthesis, cross-coupling, using magnesium without the use of the D-block transition metals would show this kind of promise or scope. There's no green color that I can use. Until Professor Heck and others showed how to deal with these unsaturated sp2 or sp hybridized organic halides. There was no easy way of incorporating these groups, so I paint these three columns red. And even the other one, these contain sp3 hybridized carbons, but still, sometimes they work. Most of the time, they don't work well. So I can give only the yellow color, no green color. Today, I can show you this one. And you see some white boxes and some yellow boxes. And then there is this troublesome 3 by 3, 9 boxes. But most of the others are green. In other words, they work in a yes manner, indeed. In other words, in high yield, in high efficiency, and then also in high selectivity. In most of the cases that we have developed in these green areas, the selectivity is usually greater than 98%. In other words, by a simple analytical method, we do not see any sign of any isomer formation or byproduct formation. Where byproducts, inorganic byproducts and salts and so on, those are not what I'm talking about. Particularly isomers, those are very difficult to separate. You don't need to do that. So some people said, well, looks like this is a revolution. And I said, well, we and others have spent a decade. The revolutions should occur instantly on one day. But I'd like to go back. So if you compare this one with the next one, okay, it may have taken a few decades, but I accept the word revolution. So we are happy, but we are still ongoing, as you can see. And here we have a troublesome boxes, but luckily we have found that in those cases you just shift the point of, if you can shift the point of carbon-carbon bond formation from the middle to the side, then we can have a green boxes. But what I want to talk about mainly today is why metals. Of course, in the periodic table there are maybe 90 or so, or close to 100 metals, besides organic elements, 10 or dozen, and then several inert gases. Most of the others are considered to be metals. Well, first of all, we all know from Arrhenians and so on, metals are fundamentally loose. Okay, Lewis. That's American name. Bear with that. Acidic. So, an acidity means electron deficiency. Very simple. And then this electron deficiency, I think, is the origin of the chemical reactivity. And in chemistry area, we sometimes swap the electron pair, nucleophile. Those are the reactants, and we push electron pairs and so on. But I would like to pull electron pair. So acids means chemically reactive. We can see that if you mix these two octets, both are octets, no low-lying empty orbital, nothing happens if you mix alkanes with alkenes. But if you can convert this into carbonium cation, carbocation, Then here you see an empty orbital, and then they react very readily. So in a way, this is sort of a metallic character. But it bears a positive charge, and they are very unstable, and so on. Now you can replace this one with isoelectronic borane. Then that's the Professor Brown's hydroboration. And very analogous reaction, but this occurs very readily, even at minus 0 degrees, minus 50, minus 78 degrees, very rapid, thanks to the availability of this one. Okay, and the same is true with the related hydrozirconation, 16 electron species. So I think we should believe in the power of this empty orbital. And but then I recognized acid and base, when you bring them together, they will bang to form a 2-electron bond like this. But there is something that is not perfect. So just think of this halfway situation between this and this. And then if you look at this thing, the base has begun providing a pair of electrons to A. Then that B starts losing electrons. Then that means leading to the partially positive species. This partial positive charge will start attracting back these pair of electrons. Likewise, A, which is without any electron here, but as it accepts this pair, then it will be charged negatively, and the negative charge will start repelling electrons. So intuitively, there is something fundamentally difficult about it, even though eventually thermodynamics takes over, and then it may be formed, like amine, borane, salt formation, and so on. And I checked with one of my physical chemical colleagues, and he looked really puzzled. But luckily, a while back, he came back to me, and then he said, "You're right." So if you analyze, this actually comes from JSCS full paper, published just several years ago. So in addition to this attractive force, there is this repulsive force as one of the two major component, and overall, even though overall is favorable. So what this means is that simple acid-base interaction has a high kinetic barrier. Even though thermodynamically it may eventually go, on the other hand, if you switch from main group metal, say boron or magnesium, to D-block transition metals, I tend to believe that these 24 or so D-block transition metals to be some of the most talented bunch in the periodic table. Well, besides being, of course, some of the most useful bunch, titanium, eyeglass frame, and all the way through chrome, iron and the nickel and chromium, that's a stainless steel. Iron, of course, is a fantastic, fundamentally very, very important. And there's a copper, coinage metal, copper, silver, gold, shiny gold, and then the platinum, and so on. So as material, they have already proven, and we cannot live without them. But a bunch of us, including Professor Heck, myself, Suzuki, Sensei, and others, over the past 30, 40, 50 years ago, and of course there are some experts here sitting near me, a bunch of us found the D-block transition metals to be some of the most talented, chemically talented elements. And I think we have found that, and we have used them. We have developed all kinds of previously unavailable chemical reactions. I think this is probably the single most important elements in this recognition by Nobel Foundation this year. But if you look back over the past 10 years, over the past decade, Nobel Foundation Committee has kindly recognized this area 3 times. First in 2001, Noyori, Sharpless, and Knowles. They indeed used various different kinds of D-block transition metal. Sharpless titanium, Noyori, rhodium, ruthenium, and so on, likewise. Knowles. And then in, was it 2005 or 6? 5? Grubbs and Schrock and so on. So Grubbs used ruthenium or late transition metals, and then Schrock used the group 5, group 6 elements. So you know that, and then this time palladium, and maybe a little bit nickel hidden, maybe. So if you think about them, there's no question that these D-block transition metals are some of the most wonderfully talented chemical species, reactive species. But the question is why? Well, actually, the answer had already been provided by some of our predecessors, who themselves, most of them, have also been recognized by the Nobel Foundation. Over the years, over the century, what Nobel Foundation has done is really enormous in our research activities. More and more, we seem to do things, some of the best things, based on works of the Nobel Prize winner. This is absolutely true. Okay, so in this case, first one, unlucky. Fukui, frontier orbital theory. Based on that, Hoffman at Woodward developed the orbital symmetry consideration principle. And in my case, since I started dealing daily with D-block transition metals, every day, without exaggeration, I look at this duo's so-called synergistic bonding. I told you that a simple acid-base interaction, one-way interaction, has a problem. Thermodynamically okay, but kinetically may be okay. But kinetically, the barrier is high, too high. But if you can have, this is base pi electron, base acid interaction, one way, just here. So that alone is a problem. But if there can be a counterbalancing, so countercurrent, counterbalancing, this dehybridized orbital with if it can provide the 2 electrons back donate to the pi star orbital, then as you can imagine, this charge polarization this way and that way can be canceled, more or less, at least partially. So that will have a very significant effect kinetically. So that's what these people have said, this pioneer. And here, for instance, this one is an alkyl iodide towards Grignard and so on. Maybe you might think that this is more reactive than alkynyl iodide. But now, towards palladium, the situation is totally different. This bond, alkynyl iodide bond, is, we estimated, to be at least 500, maybe 1,000 times as reactive in this situation as this alkyl iodide, which we may have learned to be reasonably reactive, for instance, towards Grignard reagents and so on. But now we can completely reverse reactivity, and we can do wonderful things. So this synergistic bonding is is really the key that transition metals can readily provide. But that's not all. Actually, if you go back to Brown's hydroboration or hydrozirconation, actually, we do have some of that. So this is what we were talking about. But so here, a HOMO-LUMO interaction, electrons, perhaps you might say, flow upward. And then that can be counterbalanced if you consider this sigma orbital and then the pi star orbital. So in this way. So this is okay as long as we can have this counteracting motion. What this scheme, if you accept that, should apply not only to hydrometallation. It doesn't matter what you have here. You can have a carbon metal bond. Then this should provide at least thinking, foundation for thinking discovery. And for carbometallation, actually the pioneer in this area is Karl Ziegler, 1963 Nobel Prize winner, who started this Ziegler-Natta polymerization, a tremendous, gigantic industry. And for that matter, you can also replace this hydrogen or carbon with anything, halogen. The Professor Suzuki is not today here with me, but there's a reaction discovered by Lappert in England in 1964. He didn't do much beyond that. And then years later, Professor Suzuki picked it up. And so here in his case, this is a bromine and this was a boron. The bromoboration. Normally, this kind of halometallation should be viewed as a contra thermodynamic process. So thermodynamically, it should be the opposite. It shouldn't go. But because of the high electronegativity of boron, that becomes thermodynamically downhill. And then bromoboration can take place very readily, kinetically very readily. So we take advantage of these kinds of things, and then so here reductive elimination process is a crucial step in cross-coupling. And as I was telling you, hydro-carbo haloboration, this simple addition reactions that Professor Heck just touched on. So these reactions become also very favorable. And then a migratory insertion is a very fundamentally important processes, and some others represented by Waka and Tsuji-Trost reaction. So if you are aware of these several patterns, then you can start playing a lot of games. And maybe you can start discovering. I will skip this one. This is a detailed explanation of transmetallation. Next slide. Okay, so, and I will also skip this genealogy of palladium-catalyzed cross-coupling, which has already been described, and then, of course, Nobel Committee is very well familiar with this. Next one. And the point that I want to talk about is high selectivity. So, for instance, before us, it was very, very difficult to synthesize these EE conjugated dienes, or EZ, or for that matter, ZZ, which is not shown. Today, we can synthesize all of them in completely, I should say, completely, because you don't see the other isomers by NMR or usual spectroscopic methods in a completely selective manner. If you use palladium, the platinum, we also tried platinum, it works, but too slow. So if you use nickel, this E, about 95% in this case. Here we're using aluminum as a metal because hydroalumination can be used to our advantage. And EZ becomes even more difficult, and with nickel, 90%. And the ZZ is even more difficult. But if you switch to palladium, greater than 99, greater than 99, that's the beauty of using palladium. Then we wonder, okay, so we found, we and others, of course, palladium to be superior to nickel or platinum or some other metal. What about the scope with respect to this what we call a counter cation? In other words, R1M, M over R1M. And then we screened. I always carry periodic table, and this morning it was not intentional, but I happen to have my periodic table here. And I think it's always useful, even though I can write most of them. Okay, yeah. Still, to look at it is yet another dimension, and I recommend that. So usually around me, here in my pocket, and another one in my briefcase, and a third one. It's true. So we ran the gamut, And in this exercise, which we published in 1978, we found the zinc to be probably the fastest and the highest yielding, but the boron is slower, but yield is was comparable. Tin was also the third best, but I am concerned about its toxicity issue. And interestingly, it led to this name, and this led to this name, and this led to this name. Next one. This was published in this paper. Next one. And the beauty of palladium or many D-block transition metals doesn't end there. And these are the kinds of cross-coupling that we and others would like to accomplish. And SP2, 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 SP, and so on. And we just chose these 5 cases as representative cases. And you can make these kinds of compounds, as you know, in very high yield. And what we became interested in only several years ago, rather recently, is how catalytic are they? How catalytic they are. And boy, they are very, very highly catalytic. And as you can see, we just simply determine what we call a turnover number. How many times one atom of a palladium catalyst will go around and around, and how many molecules of desired compound one palladium atom produces. Well, this 10 to the 6 is a million. So in each case, we managed to go beyond a million while retaining the product yield at a reasonable level. If you can lower that level bar, of course you can go higher and higher, but that doesn't mean much. So this translates to the high economy. If the catalyst like this, containing these ligands like this, cost $1 million per mole. No, never. Some may approach. Then even so, the actual cost is $1 or $1 or more. And anyone can pay $1 more. So that's not an issue. Okay, so I think it's about time for me to start wind up my talk. But So I told you that alkenes, and now we claim that we can make almost any kinds of alkenes, any types. Maybe there are some special factors preventing our synthesis. That's shown here. And before us, there was this so-called carbonyl olefination. So it starts with a carbonyl compound, and you go through addition elimination. This process is a problematic. It can go this way, that way, and so on. So this is represented by Vedic reaction, Vedic olefination, which was awarded the Nobel Prize in 1979, along with Professor Brown. But we don't go this way. This is a traditional way. We go from here, alkyne. There's no stereochemistry. And then usually this end and that end can be widely different. And what we do is, as I was telling you, carbo-hydro-carbo-halo-metallation. Those are concerted processes. So they are very nearly 100% synthetic. So we can go from here to here, and you can be certain about the stereochemistry of this thing, and quite often regiochemistry as well, to the extent of 95% or higher. And then you do this Lego game, then you get exactly this. So I will start winding up my lecture, let's say, with this example. So here you have a very, if you are not a synthetic chemist, then this molecule may look incredibly complex. And these are tri-substituted alkenes, which are previously rather difficult to synthesize selectively. But there's no problem as long as we use carbometallation cross-coupling. This one is E, this one is E, but this one is Z. The Z one, until several years ago, maybe decade ago, or several years ago I should say, until recently actually, it was rather difficult to synthesize. And then in this case, we resorted to Suzuki's bromoboration. As I was telling you, this kind of reaction was probably considered to be contra-thermodynamic. In other words, this thing can readily undergo elimination to go back. But in this case, yeah, that's there. That's dangerous there. But this particular reaction is not thermodynamically favorable in this way. And then, being this elemental metallation, like hydrometallation, carbometallation, and this one is essentially nearly 100% syn. There was a problem in Professor Suzuki's group, and selectivity went down to 90%, but we can retain if we do it right. And then we can just start playing the Lego game, hooking up this piece, and you get this one, and so on. So when we synthesize this part, I want you to note now, in view of time, I just point out, this one is pure. Simply, when we say 98% or higher, by ordinary analytical tool, NMR and so on, we don't see the other isomers. Pure, and this one is pure, and so is this. So no matter what we do, we can stay with a pure compound, stereoatomic, pure compound. And this is how this so-called side chain of microlactone A was synthesized. And this is, if we can do that, and to construct this thing looking back, we use palladium-catalyzed cross-coupling 1, 2, 3, 4, 5 times. And we use hydroxygenation 1, 2 times. And then we use the bromoboration here, as shown here. So these kinds of reactions do work in some of the most complex cases, in essentially perfect way. This is a CoQ10. Some of you may buy. This is the one that was very difficult previously. In other words, if you start counting from this end, 1, 2, 3, 4, 5, 6. So 1, 5, 5 doubly skipped diene. They presented a very difficult problem. And about 1969, so 40 years ago, French chemists came up with a very elaborate method to form this bond, the middle one. As long as you try to form middle one, then your struggles continue. So we figure that now we are in a position to form this bond, or this bond for that matter, where this is better. Then we switch that. And it works like charm. As I was telling you with this one as an example, this side is 500 times or 1,000 times more reactive than this side. So you take care of this one, and then you metallate this way. And in this way, all you need to do to synthesize this one in 26 overall yield, % overall yield in 9 longest linear steps. Shoei Lu prepared this thing in just a few weeks after assembling these A, B, C, D pieces. And I don't have time to go through, believe me. And we stayed always this 98% E. And someone is actually trying to industrialize with this thing, one of my colleagues at Santa Barbara. Okay, so this is the extent of my lecture today, and I'd like to go all the way back down to the end. Oh, sorry, yeah, okay. So in the area of palladium or nickel catalyzed cross-coupling in my group, about over 100 people have participated, including, I noticed Dr. Guanzong Wu, who was Professor Heck's, one of the last PhD students, who then came to me as a postdoc. Where is Guanzong Wu? Yeah, here he is. Anyway, but I still think that first quintet, which was dominated by maybe Japanese names, but I owe them a lot. And so those shown here, they are the major contributors. I don't want to demean, you know what I mean? But Dr. Takahashi, who is here in Stockholm, you may know this Jim Tour, and Shenmi Ma in China, and I already mentioned Guanzong Wu, and so on. Next one. So this is zirconium titanium area, which I did not discuss today. Let's go to the next one, more recent contributors. Well, I must confess that on left-hand column, one nation has begun dominating. So that is, I think, the world is essentially one. And anybody can, that's what I say. And through competition, I think they seem to rise. And finally, I'd like to thank National Institutes of Health, National Science Foundation, and then Purdue University, along with several industrial organizations. Thank you very much for your kind attention.